Discussing two presentations that are both in the same context, self-supervised robotics learning, self-supervised semantic understanding of robots. In plain English, can we train a robot to do what we want it to do without explicitly training the robot every time when there's a certain task, without explicitly training the robot for a certain environment, and without explicitly training the robot for a certain embodiment? In other words, whether it has one arm or two arms or no arms, whether it's a car or a humanoid robot or whatever it may be, can we find a way to train something like that in an unsupervised way? The upside of doing something like that is that we can do it at low cost and high speed, and that we can bootstrap the system so it can learn enough to be able to be deployed. And then through the deployment, we can potentially even learn more and faster. Both presentations are in that context. What's interesting about them is one is about 4 years old, the other is brand new. It's a beta paper by Sergey Levin, Drew Batra, and a couple of other people from different universities. The first presentation is from Abhinav Gupta, and it's about 4 years ago. The reason I chose to discuss this presentation is because Gupta's company just came out of stealth mode and got a 1.5 billion valuation. And I thought it would be interesting to go and see what he's doing and why potentially he could be an interesting investment target. Now, the company's in stealth mode. Their blog, Skilled AI is the company. Their blog doesn't say much about what they're actually doing. So I thought the best way to understand what people are doing is just go back into their academic history and then see what they did, because no matter what, people tend to keep doing something at least similar to what their academic history has been doing. So that's what I did. So I'm gonna, the links are in the show notes. Both presentations are, I think, terribly relevant today because we're talking about foundation models. This is Foundation Models for Embodied Decision-Making Agents, Part 22. We're also talking about self-supervised learning. We're talking about the potential for deploying a robot fleet and then learning. That's really the key. And we're also talking about the Robinson Crusoe robot. So there's a lot of things coming together here. Finally, one thing we want to discuss is the potential also for Tesla. And in particular, we want to discuss transfer learning. And then there's this fundamental question that I thought about this today, and this is definitely a question I want to put out to Tesla in the future, which is it conceivable that a humanoid robot actually learns from FSD and vice versa, and that all we do is translate the ego camera into whatever embodiment we have? That's something that the Mint paper, that's the second paper, actually is alluding to. That's also something that Abhinav Gupta is talking about in his presentation. Okay, so let's start with Abhinav. So this is 4 years old. It's a presentation at MIT. He's talking about self-supervised learning for robots. And this is pre-GPT, this is pre-transformer, this is pre a lot of things that are very common today. Vision language models, this is pre-large language models, this is multimodal foundation models. Nevertheless, it's interesting, and it's really important to go back in history to understand where people come from, because all this knowledge that we have today, it roots in the kind of knowledge that Abhinav is talking about. And in some ways, he was ahead of his time. In some ways, he was, way backwards. But that's okay. Everybody is in that kind of world. Here's the fundamental idea that Abhinav is trying to convey in this presentation, which is, can we teach a robot in a general way to do stuff? And in order to do that, we have to find a general representation of things to do. So is there maybe a lower level or general description or representation, actually that's the word, that encompasses grasping, pushing, opening a bottle, and all the other possible tasks that a robot could be doing? Is it possible to represent that in a more general way? And if so, train the robot in that way, in a general way, and hopefully get to a point where we can deploy a robot fleet and then have that robot fleet generate more data that can be used for learning. Now, I want to just a few of my own thoughts here. Number one is always the question of what is the ground truth? What's the reward model? What is a good way to open a bottle? What is a good way to shelf something? Like if you're an Amazon robot that is putting stuff from one bin into another, what does it mean to do this right? Some of these questions might be obvious, some of these questions might be less obvious. The point here is that we need to have a reward model, whether we use reinforcement learning or not. We need to have a way to describe what is good behavior so then the robots can learn. So this is definitely one question that Abhinav is trying to answer in this presentation. Another question is the data itself. Where do we get the data from? And what they're actually doing, which is very interesting, is they're trying to do self-supervised learning in a self-supervised way. So they have the robot literally randomly trying to grab a bottle, and whenever it grabs the bottle, it gets a positive signal, and that way it generates its own data. So this is an idea that I've seen with Shura and Song, an idea that I've seen with Sergey. So this is definitely proliferating throughout the scientific community, and even today. It's generate your own data. This is how kids learn, right? Little kids, they start doing stuff, they break stuff, but they start learning. That's one thing. The other is imitation learning. Now, imitation learning, of course, is a big one because that's how Tesla has trained its own cars to drive. Fundamentally, what we're trying to achieve here is to have a scalable way to generate high diversity data. This is one of the biggest insights from his presentation, okay? This is the first time, to my knowledge, that somebody has mentioned transfer learning in robotics. In other words, when we have multitask training of a robot, when a robot is taught how to push and how to grasp, and let's say you give 2,500 examples of pushing and 2,500 examples of grasping, supervised learning, you will have a better performance in pushing and grasping than if you have 5,000 data points of just grasping or 5,000 data points of just pushing. This is something that we've spoken about at length now. The biggest insight at CVPR was exactly that. And the way we interpret it is that it's all about navigation. And this leads me to a conjecture that is potentially, you see, the potential navigation problem could be actually exactly that general representation of any kind of problem. So in other words, anything that moves in the real world is potentially just solving a navigation problem. Now, it looks a little bit more complicated than that because, let's say we humans, we have 4 limbs and we have a body that has to move around. We don't want to hit stuff. We don't want to be hit by stuff. So there's a lot of things that need to be taken into account. But fundamentally, this could actually just be a navigation problem. And my conjecture is that, is there even a possibility that you can train across different embodiments? So not just different tasks in different environments, but even embodiments, and then just translate the egocentric camera and the positioning of the actual moving parts to where they need to be. In other words, if I have a car, then the moving parts are the tires. And the car has a certain geometry. If I have a humanoid robot, then the moving parts are the limbs and the legs. Again, the rest is a certain geometry. And potentially, I could just translate the egocentric camera or the information from the vision that we're gathering, which is, that now I'm talking, this is part of the second paper, the Mint paper, but it doesn't really matter. I think both of these presentations are similar enough that I'm not going to go separately all the time. I'm just going to mix them up. We have multimodal instruction, learning, Mint. The T is for tour, so Mint multimodal instruction tour, doesn't matter. The paper explains what that means. Fundamentally, the idea is that we instruct a robot to go after the counter and find a bottle there and bring it to me. So it understands this because it's trained on a visual language model. It understands what after the counter means. It goes after the counter, looks for a bottle, picks it up. So it knows how to pick up the bottle and then bring it to me. It knows what it means to bring it to me. It also knows where I am. This is what Mint is trying to achieve. And the way Mint is achieving this is by having a multimodal foundation model. So it has vision information and it has semantic text information. So it understands what it means to be after the counter. It understands what it means to bring something to me. I find it very fascinating that Abhinav Gupta 4 years ago has already learned what we've learned at CVPR, which is that there's transfer learning across different tasks. The North Star is a general model that generalizes across tasks, across environments, and across embodiments. What's that mean? Tasks, it can grasp, it can push, it can pull, it can open bottles. Environments, it can do it in my lab and in your lab, it can do it in the desert, it can do it in the snow. This is very important. Abhinav's talking about the biased learning. So you have certain environments. For example, the Berkeley lab always looks the same. Maybe it's just learning, stuff in the Berkeley lab, which has nothing to do with the actual task. So you have to be very careful. We have to have a lot of diverse data to make sure that we don't bias. The more diversity, the less bias. This is like in politics. Now, and across embodiments, I think this is the biggest one. That means that we could have a model that potentially works with a one-legged robot, two-legged robot, one-armed robot, two-armed robot, no-armed robot, car, humanoid robot, non-humanoid robot. All we have to do is translate the egocentric camera, assuming it's trained just on vision, into its actual embodiment. Now, what the Mint paper is fundamentally also trying to do, there's a very important question that I want to now tackle, and I want to finish with Tesla. So the question is the following. We can have high-level information about tasks. For example, go pick up the bottle, drive me from Los Altos to Palo Alto, fly the drone across a certain parkour. Those are high-level tasks that I think at the stage where we are today in transformers should be semantically understandable. And we've spoken also about the necessity, let's say, for Tesla to add semantics to its vision stack. So we know that elementary school is a risk factor that the car should be particularly careful about. Maybe drive slower, even if there's no signs, just because it knows there's a school, like things like that. Now, what's even more interesting is, can we combine that semantic understanding with the actual low-level actuator understanding? Because that's really what it's all about. Fundamentally, we need to, like I've spoken about this just, I think, 1 or 2 presentations ago. My 15-year-old son probably has a good semantic understanding of the world, but he doesn't know how to drive. Like, he has to still learn how to drive, and the same applies to a robot. The robot has to know how to drive. It actually has to know how to which actuator to push, which brake to not use, or gas pedal. The humanoid robot has to understand how it actually moves the arm from left to right. It actually has to be able to do that. So what Mint's trying to do is combine the high-level semantic understanding with the low-level actuator understanding, combine that. We believe that one of the biggest advantages of Tesla is that they have a car that is driving, and it's imitating not just the driving of people, but it also has information about the actuators while it has the video. So the video and the actuators are synchronized by default. That's by design. And we could get the same thing with a robot, with a humanoid robot. We could get the same thing. And this is part of Abhinav Gupta's chicken and egg problem, or, Sergey spoke about this also. If we had robots in the field, we would have semantic understanding and actuator understanding in one. But until we get there, we have to kind of find a way to combine them. And our hope is that maybe Tesla can already do this with FSD. In other words, use FSD to train robots how to grasp. Because in principle, at a very low dimensional representation level, turning around the curve or driving around the roundabout or whatever could be the same problem like opening a bottle. In a sense that it's a navigation problem, and all the robot has to do is just see a bunch of more data of how to actually open a bottle, but it knows how to learn. It knows how to learn how to open a bottle. So in other words, it knows how to train itself how to open a bottle because it knows how to navigate. It knows how to navigate its limbs, and it knows how to turn actuators on and off to accelerate or decelerate a certain task. This is, I have to admit, this is definitely new territory for me. It's an important presentation. It's one of those I'm going to put a heart on because this is, I believe, like this is one more step towards generating new knowledge here. Because this episode that I'm recording right now, in my opinion, is going to open up a lot more new questions that it's answering, which is exactly what I think good episodes do. Maybe it's frustrating for some people. The purpose of this podcast here is to give people a sense of what it feels like to run a hedge fund. So it's not to generate knowledge or publish papers or get a Nobel Prize. What we're really trying to achieve here is open up people's minds towards the task of wealth generation. And in our case, this is AI and real world AI, but I hope people can translate from here and understand what it takes to get the kind of knowledge and to even work towards gathering the kind of knowledge or gathering the kind of conviction that is necessary to generate wealth. So to summarize, again, this is an episode that has a lot of open-ended questions. The most important open-ended question is, can we have a general robotics model that is trained across tasks, embodiments, and environments, and deploy it in a way that we also have a semantic understanding, high-level semantic understanding, and a low-level actuator understanding? And can we do this in a self-supervised way so that way we can generate our own data, which is, in principle, we're teaching the robot not just to learn stuff, but also to learn how to learn. I think we have an understanding of what it takes to learn. We have that understanding between the transformer technology and the diffusion technology and all the other generative AI technologies that we've developed in the last couple of years. I think the understanding of how learning works is, we're pretty good at that. What we need now is an infrastructure to put that all together, to generate enough data at a certain speed and scale and general enough so we can deploy a bunch of robots and then start learning from them. I want to finish with Tesla and just ask myself first, can Tesla use FSD and extrapolate to the humanoid robot? Is there enough chance for learning there? Now we know there is some chance for learning, but do they still have to go task by task or teleportation by teleportation, which it looks like they're doing right now? Or can we maybe have a more general representation of the driving stack and then transfer it to the humanoid robot stack? And the reason we are so keen on the driving stack is because we have the data. We have billions of miles of driving, so we have ground truth of what it means to be a good driver, at least to be a human driver. We understand that, and now we can, and we have not just the high-level semantics. In other words, we know what it, turn right, turn left, all that stuff. Stop at the red light, even though I don't know what the red light is, but I'm stopping at the red light because I learned over millions of iterations that that's what I need to do when exactly this type of scenario presents itself. But I also have the actuator information. With that, I could probably bootstrap myself and accelerate the robotics business also. And finally, I want to say also something that Abhinav said very importantly. We need low-cost robots at scale. We need standardized hardware. We need standardized actuators. We need robots that don't break as fast. We need software. We need batteries. We need a deployable inference at the edge, which is not draining the battery, which is not breaking when the robot fails. Like all of these things, which we believe Tesla is working on. And that's, in the end, that's going to be more important than the most fancy algorithm.